Well, the hemispherical chamber, as the name implies, is a portion of a sphere, and here you can see the arc shape of the sphere itself. With this, we can bring the spark plug in to the center of the chamber, which is an excellent position for the spark plug. The same shape over in this view allows us to put the valves in a position where when they open, like this inlet valve, it has excellent breathing of the air past the valve seat. Likewise, when the exhaust valve opens, there is excellent breathing of the exhaust gases to go past the exhaust valve seat. And this combination then has an excellent volumetric efficiency for the engine. So now we have a chamber that is truly excellent for power. And that's why we like that hemispherical shape. Well, when we started design of the latest Hemi in 1963, we used one critical dimension that had proven itself on the prior generations of engines, and that was the angle between the intake and exhaust valve. The angle from this valve, the intake, to this valve. We set that angle at 58 degrees. The older engines were 58.5 degrees. But that dimension allowed us then to move very quickly on the design because we knew from all the prior research work that those valve angles and the valve breathing was going to work the best. And when we put the valves then into position in the design, we were concerned, though, about whether they should be symmetrical about the bore center or whether we should move them inboard. We opt to move them inboard the way they are now, and you can see the exhaust is here, in order to minimize the length of the exhaust valve rocker arm. Had we left the exhaust valve further out, that rocker arm would have gotten longer and we would have had problems with valve dynamics. So that was the critical point from the old engines that we put into the new engines, as well as the basic approach of the Hemi engine. The reason I got started with Chrysler is because Chrysler sent a recruiter to the college that I graduated from, which was Yale University, and Chrysler offered an excellent program of having 2 years as an engineer in training, where we would go to classes part-time and we would have on-site real job part-time. So that gave us both additional academic training, and it resulted in a Master of Automotive Engineer after the 2 years were up. Plus we had experience in working in a number of different departments throughout engineering and even some production experience. And then after the 2-year period would be over, then we could make a job selection, where we would then opt for one of any department within engineering or any place that we may want to work as a permanent assignment. And with that kind of an opportunity, it was truly an offer that was very attractive, and I took it and came to Chrysler, and that was in 1947. And so I graduated from that Chrysler engineering program in 1949 and went as my permanent assignment to the Plymouth assembly plant. I was working for Chrysler, but I was not involved in engines at that time. Right. I knew my future boss happened to be working at the Plymouth assembly plant, and there was a fellow named Bob Rary who was in the engine section. And it was always kind of interesting to see the fellows working with the engines, because that was real mechanical engineering work, and I was a graduate in mechanical engineering. So later, when the opportunity came to me to transfer from the work I was doing at the time, which was in electrical work, engine electrical work, over to the engine design section, I jumped at that opportunity. Yes. Well, Chrysler had a long involvement in engines, of course, going back to the beginning of the company, and that was part of their legacy of having very modern engines when Chrysler was originally established. During the Second World War, they worked on a very large aircraft engine, a liquid-cooled aircraft engine that was named the XIV 2220, the 2220 standing for the displacement of the engine. It was an inverted V16. The combustion chamber was a hemispherical chamber, and it was 2 valves and an overhead cam. And Chrysler worked on that engine in their labs in the 40s during the Second World War, and it was installed and flew in an airplane at the end of the war, but the time of piston engines was over then. However, Chrysler gained a lot of experience from that particular engine. As I said, it was a 2-valve HEMI engine. When they started working again on the passenger car engines, I'm sure, although I don't know, haven't talked to people, but I'm sure that that kind of knowledge carried over. So then Chrysler experimentally built engines that had HEMI heads, 2-valve HEMI heads on them. First one was an inline 6-cylinder engine. And that, again, was a very experimental engine, and they liked the results of that so much that they wanted to put those kind of cylinder heads onto V8 engines. So from the inline 6 came the V8 engines. Now this was in the period of the late 40s. Now we're just after the war was over. So engines were then designed first by research as a V8 HEMI head engine, and then with the results of that, then a production design was prepared. The first production design became the Chrysler line HEMI head V8 engine. And that's the one that then was released for the 1951 model year. And it was then followed up immediately with an engine for the DeSoto, which was a different engine, but sharing the basic type of cylinder head, which was the 2-valve HEMI head engine, in 1952. And that was then followed up the following year for Dodge division, which was again a HEMI head 2-valve V8 engine. Each of those engines were built by their respective divisions. They had the machine tools to build the engines. Those engines all had the kind of power supremacy that Chrysler liked over the wedge head inline valve engines of other designs. And I remember when the engines were advertised and as HEMI head engines with the attributes of the power that the engine generated. Chrysler had been involved in racing with the prior HEMI engines, particularly the Chrysler and the Dodge HEMI engines. I remember Dodge being raced by Carl Kiekhaefer. And those engines had done quite well. Well, the engines went out of production when we introduced our new big block engine, which we referred to as the B and the Race B engines. That was in 1958. Those were wedge heads, though. We did do some racing with the wedge heads and did fairly well. However, it was clear as the years went by that we were not competitive, particularly on the closed circuits like the Nascar circuits. What I remember was that our performance group that Tom Hoover was part of and Bob Roger was in charge of really said that either we've got to do something big or we should get out because we were not having any enough good wins for the corporation to make it worthwhile. And then Tom Hoover and his group put their heads together and said, to do something big, we should bring out another HEMI. And so we had the challenge in design to make a HEMI head version of our big block engine, which only had a wedge head on top of it. That was the design challenge. And with that challenge, we made some feasibility studies early in 1963. And as I recall, it was March of 1963 that we were told to go ahead. And with that go ahead, then we launched what became our HEMI engine program. We assigned our best designer to the task, a fellow named Frank Bilk, and then Frank made the final layouts. He used the HEMI principles, of course, the hemispherical shaped chamber, placing the valves on the chamber, and he had a particular challenge on the intake valve, I should say the intake port of the cylinder head. To go back, the old HEMI heads had a 4-bolt head pattern, and they could bring the intake port directly into the chamber. But our new engine was designed with 5 bolts, and the 5th bolt was right in the center or where we would want to bring in the intake port. We liked the 5-bolt pattern because it gave us more clamping pressure for the cylinder head, which we knew we would need for that engine and any future variants of the engine. So we did not want to lose the 5th bolt. Frank made a major breakthrough when he thought of an idea of bringing a bolt up from underneath into the port. And that was truly a brilliant solution to the problem, because when that was done, then we had the full freedom of making that intake port almost as big as we wanted to make it. That was the real breakthrough on making the HEMI head out of our raised B engine. When we started our final design in March of 1963, we knew that our target date for that engine was the Daytona race of February 23rd, 1964, obviously less than a year away. We knew we had a tough job and a fast job to do. We started procurements of the individual parts as fast as the designs were completed. We had available to us experimental pattern equipment for many of the major parts for the B and raised B engines, which were now in production. We were able to make changes to that equipment so that we could get parts quickly. However, the cylinder head was a brand new part, and we had to make all new equipment in order to make castings for the cylinder head. We had the cooperation of everybody at engineering. Truly, it was a unified effort by engineering and our suppliers to get those parts all together for the race. As it turned out, we were able to get all of our parts together for the buildup of the first prototype experimental engine by the end of November of 1963, and the engine ran under its own power on December 6th of 1963. It was about 3 months away. February 23rd of 1964 was race day. But of course the engines had to be ready weeks in advance of that to get them in the cars and do all the preliminary work. Now we're starting the development of the engine. It's on the test stand, it's producing power. The engine was what we had hoped it would be right from the beginning. We were getting the power out of that engine. Of course, as soon as the engine started to run, then we were doing development for performance of the engine, and we were doing development for durability engine, because the Daytona race is truly both a performance and a durability contest. And we ran into problems with the engine on the durability side. By the end of January, we found that we were cracking cylinder bores. And we were cracking the bores in a very specific location. I can show it here. We were finding cracks up and down the bores at the point where the piston, and this is a cross-section of a piston that's sitting in the bore, where the piston piers would rest against the bore wall of the cylinder. And this was on the right-hand bank, and this is the thrust wall of the cylinder. And this is where the cracks were occurring. We knew there was only one way to fix that crack, and that was to make additional castings that had a heavier wall. And that was the challenge at the end of January. And when we found these cracks and realized what the solution would be to get additional castings, cylinder block castings with heavier bore walls, we were then about 3 weeks away from race day. So this is what we did. We made some templates so we could go down to the foundry, which was in Indianapolis, Indiana. It was a Chrysler foundry where we made all the cylinder blocks. And we would take existing water jacket cores and we would rub away sand with our templates. And as we would rub away sand, that would allow more metal to occupy that space and make the bore walls thicker. It's going to be very simple. However, when we made our first castings and the metal was poured into the mold and the castings were shaken out, and we looked at them. There were large amounts of metal that were missing. It was as if we had had a minor explosion inside the mold before everything was solidified. So we sat with the foundry people, who were excellent, of course, at this, and we said our best guess at this is that when we made the water jacket cores that had the sand rubbed away, and we put these into a solution that gives a very dense surface to it, that we did not allow enough drying time for this solution, and that there was still moisture in those water jackets when we poured the metal in. We'll have to try more drying time, and we'll try it again. Well, we did that in a succession of times, and we did that about 3 or 4 times before we finally got satisfactory castings at the foundry. To do that, we worked day and night in the foundry, and I was one of the people down in the foundry with 2 others from engineering and with a number of the key foundry people. And with wonderful cooperation from these people, we finally got the good castings, and we had those things on a truck that went not directly to the machine shop, but to a place where they could be annealed, because we had found in other problems that there were areas of the block that were getting residual stresses. So we just annealed all the blocks from that point on, and that means bringing them up to a temperature of about 1200 degrees Fahrenheit, giving them a slow cool down, and then they went to the machining plant that was at Trenton, Michigan, and there the plant manager was waiting for us almost with open arms to get these blocks onto the machining line so he could send them down the main line. After they were machined there, then they were brought to offline operations where the special machining operations for the HEMI engine were done. And then after that was completed, they were put on another truck and sent to central engineering at Highland Park, Michigan, which is where I worked and where our build-up rooms were. And there, then, finally, with these good blocks, we started to build new engines for the race. And then trucked down to Daytona Beach. These heavy wall blocks then were being built into engines as fast as we could at Highland Park. However, down at Daytona, events were already rolling, and all the qualifying was done with engines that had the thinner walls, plus the 50-mile race, which is part of the qualifying, was run with the engines that had the thinner wall blocks. We just had to keep our fingers crossed on those because we did not have time to get our heavy wall blocks there. The heavy wall blocks finally arrived between the 50-mile races and the final race, which was on February 23rd. So all the engines had to be changed in the cars, no matter how good they may have run in qualifying. We changed all the engines in the cars to the heavy wall blocks. And we were ready to race. Then we came to the race day. And what I remember of being down there is that Ev Moeller and I were in the stands opposite the pits, so we could look at all the pit action. Well, the race started, and our Hemis went out and did very well. Truly, they were dominating the race. And after about somewhere between 25 and 50 laps of race time, they all pulled into the pit, and the hoods went up. And we just about died. What had happened was that there was so much debris on the track, paper, stuff like that. It had blown into the front of the radiators, and the engines were overheating. So the pit crews just had to scrape this stuff off, close the hoods, and off they were, back again, and they truly dominated that race. Our cars were just running faster around everybody for the whole race. And of course, we came in first, second, fifth, ninth. It was a glorious feeling. I'll say that we could not relax until that checkered flag went down, because we just still although we knew it was going to finish, we always had that little fear, or I should say big fear, that something would go wrong in the process. But when the checker flag went down and that race was over, it was just jubilation. It was just a wonderful feeling that all the work we had done had come to fruition in such a dramatic way. Also a good feeling that among the winners of the race were those heavy wall blocks that we had cast at the Indianapolis Foundry on February 3rd. The race was won by a block that was cast on February 10th. And that was about the time of the 50-mile races. It was that close to get those heavy wall blocks into the race. Just an interesting part of our running the engines prior to Daytona, getting ready for the Daytona race, was that the first group of engines were sent to the racing teams and installed in the cars, and then the teams went out on the track. What they did, without telling anybody though, in order to keep a secret on how fast the cars could go, they never made a complete lap under full power. They would make half laps so they could get a feel for the car and for the engine. Then they would slow down so that our competitors and any of the officials there never could put a stopwatch on and figure out how fast those Hemi-powered cars could really go. So that was a secret that was kept right until the qualifying day. And this idea of keeping our full power a secret, and the ability of the cars to use that power a secret, was one that was thought up by Troy Simonson, who was an integral part of our racing group. Following the race, then, there was a desire by NASCAR to have such racing hardware, I should say high-performance hardware, available to really everybody that wanted to partake. And we did have a supply of hardware that went out to the professional racing folks through teams. Not a large supply, but it was there. But there was still the pressure to make this more available, and there was a desire to capitalize in a production sense of what we had been able to accomplish in the racing circuits. So the product planning people, including Tom Hoover, then promoted a plan to start a production build of our Hemi engine. Now, we knew that we could not just put a race engine into production on the street. That just wouldn't work. But we were able to make a modified version of the engine that became our street Hemi. One of the things we changed that was different, very obvious, was in the carburation of the engine. For the NASCAR circuit, it required a single carburetor with a very special intake manifold. For the street, we wanted to have a package that would be more drivable throughout the speed range, so we decided on two 4-barrel carburetors sitting in tandem on top of an intake manifold, and we would provide even a heated floor for the rear carburetor so that during cold startup it could get to the normal fuel vaporization process to allow a regular engine startup. And this was done for the primary 2 barrels of the rear carburetor. All the other barrels would come into play as the driver would open the throttle. And other things that were done, we were able to not use as beefy parts like the connecting rod as we use for the NASCAR version of the engine. We changed the oil pan of the engine because the street engine did not need we call it the wing tank oil pan that were needed from the closed circuit tracks with their requirements for acceleration around the turns. We did some different cosmetics on the engine. We gave it a crackle finish, cylinder head covers, and we changed the exhaust manifolds of the engine. For racing, we used fabricated tubing. For the street engine, we decided to use cast iron headers. They had a very nice streamlined branches, but they were easier for us to use in production, considering the vehicle assembly we had to go through. And of course the camshaft was quite a bit detuned from the racing type of a camshaft, but it was still what we would describe as a high-performance camshaft for the engine. It was a long way from what we were offering in the other wedge head versions. And there may have been some other details, but those were the primary things that we changed in the engine. Oh, I should mention another. We also reduced the compression ratio. The racing people were able to get a higher octane type fuels than what you could get at the gasoline pumps. So the ratio was dropped down to, I think it was 10.5. It still required good premium, but it wasn't the same as racing fuels. I think we had some inkling that if we were successful, we would have a very popular power plant on our hands that would get a reputation. I'll say our immediate objective that really truly occupied us was, though, that February 23rd race. We had to do a good job for that one. But we knew if that was successful, then we had a product on our hands that would have acclaim from the automotive world. Essentially, this street Hemi came into being because of the corporation's need to win that race. In 1966, SAE requested papers of the various automobile companies, and Chrysler was pleased to be able to present a paper on the Hemi engine, because this engine had then been released for use as a street Hemi engine in various of our cars. And this is the paper that I had the privilege of presenting to the Detroit section of the SAE in April 11th of 1966. And it goes into very nice detail of the engine itself, how we designed the engine, the variants of the engine, and design and the development of all the parts of the engine. It was co-authored by Bob Lechner, who was then doing the engine development in the laboratory as I was doing the design work in the design shop. This happens to be my favorite picture of the engine, and one I hope that you'll be able to get out of the archives. We're going to be in front of an audience that's come to hear about the power and the glory. So we started up the speech with an audio tape of an engine running at max power in one of our dyno labs. And they have a good speaker system, as you can appreciate, and it was a Rackham building hall. And we just thundered that stuff out. Then we had a number of film clips of the performance uses of the engine. So we had race cars going by, we had drag strip cars, I think they were doing wheelies down the strip, and then we started the speech. We really got their attention. It was great. It was really great. What caused the demise of the Hemi in 1970 was really a number of factors. One of them certainly was the bad reputation that the muscle cars had gotten by then, and the insurance companies' response to that, of their raising the rates dramatically on those cars. The other was that the racing rules were being changed and displacements were being reduced. And it was about that time that NASCAR even dropped the displacement ruling from what had been 7 liters or 426 cubic inches when we started with Hemi, down to 6 liters or 366 cubic inches at that time. And our Hemi power plant was just too big, really, to compete with that in that size category. And we were starting to use our small block for NASCAR racing then, which was much more appropriate for that size. And the other part was now the approach of the environment, in that we had to do a better and better job with emissions requirements. One of the first things that came into the emission scene, for example, was the closed crankcase. That was in 1961, a requirement for California. By 1964, it was a requirement for all cars. With each successive year, there were more demands for the engine to reduce their emissions. And we could see that the Hemi, with its size and its flavor, was going to be a particular difficult engine to qualify for emissions. So there had to be almost a business decision whether or not to continue with that level of engineering work, or whether we should say, the HEMI has done its job, let's discontinue it now. We don't want it to ever get a flavor of being a mild-mannered engine. So in 1970, we said, let's stop production. I feel very good about our HEMI engine. I feel good about all the things it has done, and certainly the attention it has gotten. It has gotten attention for automotive engine people, including designers and developers. I'm always amazed and very appreciative of the enthusiasm of the Mopar fans of this engine. It's truly amazing the interest that I have run into personally of people who want to talk about the engine, want to know about the engine, are interested in every phase in the design and development of the engine, and just are so full themselves of so much detail about the engine, showing that they have made wonderful studies of this engine. It's an enthusiasm that is a reward that I feel very sincerely.
Good. Good. I think that's good. Yeah. Good. I think we've got plenty.